August 22, 1943. At the School of Tank Technology at Chobham, England, a small group of metallurgists and engineers are gathered in a brightly lit laboratory. The air is thick with the smell of cutting oil and nitric acid. On a heavy steel workbench, under the harsh glare of an inspection lamp, sits a piece of metal that represents one of the war's most terrifying paradoxes. It is a transmission gear recovered from the drivetrain of a captured Tiger I tank. Dr. Robert Stevenson, a quiet, methodical metallurgist recruited from the naval industry, leans in closer. Before the war, his expertise was in the vast steel plates of dreadnoughts. Now, his focus is on the intricate heart of Germany's most feared land weapon. The gear is massive, a testament to German over-engineering. It measures 8 inches in diameter, 2 inches thick, a formidable piece of hardened steel. It was designed for a singular, brutal purpose: to transfer the colossal power of a 700-horsepower Maybach engine to the drive sprockets, propelling 57 tons of armor and firepower across the battlefield. But this gear has failed. Stevenson traces a gloved finger along the point of failure. It is not worn down. It is not cracked or pitted from use. A gear tooth, nearly the size of a man's thumb, has been sheared completely off. It is a clean, crystalline fracture, a sudden, catastrophic break through material that was supposed to be indestructible. This is not a new discovery. This is a pattern. This is the 7th failed Tiger transmission Stevenson has examined. Every single Tiger tank delivered to Chobham, captured intact from the battlefields of Tunisia and Sicily, has arrived with transmission damage. Some failures are minor, with bearings scored and races cracked. Others are catastrophic. This one, from the infamous Tiger 131, captured by British forces near Tunis, is catastrophic. The entire final drive assembly was destroyed. The gearbox is choked with metal fragments. The transmission failed with such violence that it instantly locked the drive sprockets, bringing the 57-ton behemoth to a dead stop. The tank was not destroyed by an Allied shell. It was not knocked out by a mine. It simply stopped. It became a stationary 20 million Reichsmark pillbox, until it was eventually abandoned by its crew. This single, broken piece of steel is a clue. Intelligence reports from the front lines have been pouring in, all telling the same story. Tiger transmission failures are common. Not just common, but epidemic. The statistics are so staggering they are almost unbelievable. More Tigers, the reports suggest, are being lost to mechanical breakdown than to enemy fire. By August of 1943, approximately 130 Tiger I tanks have been produced. On any given day, fewer than half are operational. The rest are broken down, immobilized, awaiting repair crews, awaiting parts that do not exist, or simply abandoned because field repair is impossible. This is the central paradox of the Tiger tank. On paper, it is the most formidable fighting machine in the world. It was conceived as Germany's answer to the Soviet T-34 and KV-1, a weapon that would be invincible, unstoppable. It is armed with the legendary 88mm gun, capable of destroying any Allied tank at ranges exceeding 2 kilometers. It is shielded by 100mm of frontal armor, impervious to nearly every anti-tank weapon in the Allied arsenal. In practice, the Tiger cannot reach the battlefield. 50% of all Tigers suffer a major mechanical failure before completing their first operational mission. The vast majority of these failures are not engine-related. They are transmission-related. Stevenson's job is to understand why. He is a man of science, not a soldier. He does not see a myth or a monster. He sees a problem of material science. The German engineers who designed this tank are among the best in the world. The German transmission industry is superb, and yet they have created a tank that the German industrial base cannot adequately support. The result is a weapon system that fails mechanically before it can ever engage the enemy. Stevenson begins his autopsy. He places the sheared gear tooth under magnification, examining the fracture surface. The grain structure tells the story of the metal's final moment. The fracture is brittle. There is no sign of plastic deformation, no ductile tearing, none of the stretching or warping that would indicate the metal bent before it broke. This was a clean, sudden snap. This tells Stevenson that the steel failed suddenly, under immense stress, without any warning. One moment, the gear was transmitting torque. The next, it shattered like glass. He moves the gear to a Rockwell tester, a machine designed to measure the hardness of metal. He presses a tiny diamond indenter into the gear's surface and measures how deep it penetrates. The reading flashes, 62 HRC, Rockwell scale. Stevenson frowns. This is extremely hard. It is in fact too hard. The specification for transmission gears, parts that must endure both wear and violent shock, is typically between 58 and 60 HRC. That range represents a critical balance. The gear must be hard enough to resist surface wear from friction, but it must remain soft enough or tough enough to resist brittle fracture from sudden impacts like shifting gears under load or making a sharp pivoting turn. This gear is not balanced. It is all hardness and no toughness. Stevenson tests multiple locations on the gear's surface. The readings are consistent, 62 to 64 HRC. He then takes a cutting wheel and carefully sections the gear in half, a foul-smelling plume of blue smoke rising from the blade. He polishes the cross-section and tests the core. The interior measures 52 HRC. This confirms his hypothesis. The surface is significantly harder than the core. This is the hallmark of case hardening, a standard heat treatment process for components like gears. The process, typically carburizing, infuses carbon into the surface of the steel. The part is then heated and rapidly cooled, or quenched. This creates an incredibly hard, wear-resistant case on the outside, while leaving the core of the metal softer and tougher. Case hardening is normal. It is essential. But it must be controlled with absolute precision. Stevenson's analysis shows the German process was failing. The case is too hard, but it is also too deep. He measures it, 4 millimeters deep. The normal case depth for a gear of this size should be between 2 and 3 millimeters. The excessive depth and extreme hardness mean the gear has almost no flexibility. The hard, brittle case extends too far into the material, leaving a core that is too small to absorb shock. The gear is, in effect, a shell of glass wrapped around a small, soft center. It is fatally prone to fracture under the exact shock loads it is guaranteed to experience in combat. Stevenson must see the why. He must understand the microstructure. He cuts a small sample from the gear, polishes it to a mirror finish, and etches it with nitric acid. This acidic bath dissolves the metal at different rates, revealing the hidden grain structure. He places the sample under a metallurgical microscope, magnifying it 500 times. The image that swims into view is the smoking gun. The microstructure is almost entirely martensite, a hard, brittle, needle-like phase of steel formed by the rapid cooling of the quench. Martensite is desirable. It is what gives the gear its hardness. But it is only desirable in controlled amounts, and it must be tempered. Stevenson sees almost pure, untempered martensite in the gear's case. There is very little tempered martensite. Tempering is the critical final step of heat treatment. After quenching, the hardened, brittle part is reheated to a moderate, precise temperature for a specific amount of time. This process relieves the internal stresses from the quench and allows some of the brittle martensite to transform into a new structure, tempered martensite, which is softer, far less brittle, and vastly tougher. Proper tempering is what gives a gear the balance it needs to survive. This gear shows almost no sign of adequate tempering. It was hardened into a state of extreme stress and brittleness, and then it was never relieved. It was, from the moment it left the factory, a mechanical time bomb. Stevenson examines 6 more failed Tiger gears from different captured tanks. The pattern is identical: excessive surface hardness, excessive case depth, a microstructure dominated by untempered martensite, brittle fracture. The conclusion is inescapable and damning. The problem is not isolated to one gear, one tank, or one factory. It is systemic. Every single Tiger transmission is being built with gears that have inadequate, or perhaps entirely skipped, heat treatment. They are all too hard, too brittle, and guaranteed to fail. They will fail under the normal stress of operation, but they will fail instantly under the extreme stress of combat maneuvering, the sudden acceleration, the abrupt stops, and the sharp skidding turns that are necessary to survive a tank battle. These maneuvers create shock loads that spike far beyond normal operating stress. Properly treated gears are designed to absorb these shocks. The Tiger's gears cannot. They shatter. But Stevenson's analysis, while correct, had only uncovered one layer of the failure. The skipped tempering was the immediate cause of the brittleness, but there was a deeper, more fundamental flaw hidden in the steel itself, a flaw born of desperation and a collapsing supply chain. As Stevenson and his colleagues at Chobham would soon discover, the very chemistry of the steel was compromised. German industry was being starved of the critical alloying elements that make high-strength steel possible. Tempering is what gives a gear toughness, but the alloys are what give the steel the capacity to be tough in the first place. The most important of these for high-stress components was molybdenum. Molybdenum is a miracle element. It dramatically increases the hardenability of steel, allowing a deeper and more uniform hardness to be achieved. But it also, critically, improves the steel's toughness and resistance to tempering embrittlement. Nickel, another key alloy, provides core strength and fracture toughness, preventing cracks from propagating. By late 1942, molybdenum was being systematically excluded from German armor and mechanical parts. By mid-1944, nickel had all but vanished, reserved for only the most critical U-boat and aircraft components. The steel being used for these massive gears lacked the essential ingredients. This created a catastrophic cascade of failure. First, the base steel, lacking molybdenum and nickel, was already inherently brittle. It was prone to crystalline fracture, the very clean, glassy snap that Stevenson had observed, a failure mode that showed the metal had no ability to deform or absorb energy. Second, the German metallurgists, knowing their steel was inferior, were forced to compensate. They tried to achieve the required surface hardness by making the case hardening process more extreme, making the case deeper and harder, just as Stephenson had measured. And third, the final fatal blow. The production lines, under pressure, skipped the one step that could have saved it. The skipped tempering, applied to an already inferior, brittle, and over-hardened steel, was not just a mistake, it was a death sentence for the gear. The question was no longer what or how. The question was why. Why would a nation with Germany's engineering prowess, with its army of brilliant metallurgists and state-of-the-art heat treatment facilities, make such a fundamental amateur-level mistake? Stephenson and the analysts at Allied Intelligence began to investigate. They reviewed captured technical documents, production schedules, and, crucially, began to interview captured German engineers and factory workers. The answer, when it emerged, was not one of engineering ignorance, but of systemic, institutional collapse. Germany was under an intense, almost pathological, pressure to produce. The war on the Eastern Front was a voracious monster, consuming men and material at an insatiable rate. Tigers were needed desperately, immediately. Production schedules were compressed from months to weeks. Every Tiger had to be completed as quickly as possible. And the primary bottleneck in production was not welding the hulls or assembling the turrets. It was heat treatment. The process is slow. Carburizing the gears takes hours, heating them in a carbon-rich atmosphere. Quenching is fast, but then tempering is slow again, requiring hours more in a furnace at a precise lower temperature. Each step requires time, furnace capacity, and skilled workers. By 1943, Germany was running out of all three. Time was inadequate. Furnace capacity was overwhelmed. And most critically, the skilled workers who understood the nuances of metallurgy, who knew that tempering was essential, were being conscripted and sent to the front. They were being replaced by minimally trained personnel, prisoners of war, and forced laborers. These new workers did not understand the science. They did not understand the critical importance of precise temperature control, or that tempering was not an optional step. They followed simplified procedures designed for one thing: throughput. Carburize, quench, ship. Tempering was abbreviated or skipped entirely. It saved hours of furnace time per gear. It increased throughput. It allowed more Tigers to be completed per month. The cost was reliability, but that was a problem for later. The failures would happen in the field, in Russia or in Africa, not in the factory. They would not be discovered during acceptance testing. The factory met its production quotas. The high command got its tanks. The transmission failures were someone else's problem. This was not the only source of the failure. The problem was compounded by the Allied strategic bombing campaign. The bombing of German industrial centers had two key effects. First, it directly hampered quality control. Power cuts and damage to facilities meant that even if the will to temper the gears existed, the ability to hold a furnace at a precise temperature for 8 hours was not guaranteed. Second, and more importantly, the bombing campaign forced Germany to decentralize production. To protect against single-point failures, component manufacturing was subcontracted out from the main high-quality factories like Adlerwerke to dozens of smaller, inexperienced machine shops. These smaller shops lacked the equipment, the expertise, and the quality control to properly handle the complex heat treatment of high-stress gears. This decentralization explained the inconsistency Stephenson was seeing. Some gears were too hard. Others, as later analysis would show, were too soft, their surfaces wearing smooth in a matter of hours. The result was a quality control lottery, where every Tiger transmission was assembled from a collection of parts with wildly variable and almost universally flawed metallurgy. On August 28, 1943, Dr. Stevenson wrote his preliminary report. It was a dry, technical document, but its conclusions were significant and damning. He documented the metallurgical analysis, described the excessive hardness of 62 HRC, the deep case of 4 mm, and the critical lack of adequate tempering. He identified the microstructure as untempered martensite, explaining its brittle nature. Estimated operational effect. Transmission gears will fail under shock loads encountered during combat maneuvering. Failure mode is catastrophic, sudden fracture with no prior warning. Once fracture initiates, the transmission becomes inoperable. The tank is immobilized. This technical report was a piece of intelligence as valuable as any Enigma decrypt. It revealed a fatal, systemic weakness in Germany's most feared weapon. Stevenson's final recommendation was simple: recommend dissemination to Allied armor commanders. German Tiger tanks are vulnerable to mechanical failure. Aggressive maneuvering by Allied tanks may induce Tiger transmission failure even without direct combat. The report went up the chain of command, eventually landing on the desk of Major General Percy Hobart, commander of the British 79th Armored Division. Hobart was an innovator, a man who understood that destroying enemy tanks was not just about firepower. It was about exploiting every weakness. If Tiger transmissions failed under stress, then Allied tactics should be designed to create stress. Force the Tigers to maneuver, force them to turn sharply, to accelerate and decelerate. Every sudden change in direction, every panicked pivot steer, increased the probability of a shock load that the brittle, untempered gears could not withstand. Hobart circulated Stevenson's report to armor commanders, classified secret. It included new tactical recommendations. When engaging Tiger tanks, it read, attempt to force aggressive maneuvering, flanking attacks, rapid position changes. Create situations requiring the Tiger to turn sharply or reverse direction. These maneuvers stress the transmission and may induce mechanical failure. A Tiger with a failed transmission is a Tiger removed from the battle without expending ammunition. When the recommendations reached field commanders in September 1943, some were skeptical. The idea that you could defeat a 57-ton monster by making it drive seemed absurd. Tanks were designed to move. But during the grueling engagements in Italy in October 1943, British tank commanders began to report unusual observations. Tigers, when flanked and forced into aggressive maneuvers, would sometimes just stop. Not hit, not burning, just stopped. The crews would bail out and abandon them. Later examination by recovery crews showed catastrophic transmission failures. The pattern repeated in Sicily, in Italy, and later in the hedgerows of Normandy. Tigers were breaking down during combat at rates that far exceeded normal mechanical failure. German after-action reports described the problem, but they attributed it to combat stress or poor maintenance. They did not realize the root cause was metallurgical. They did not know that every Tiger transmission was a time bomb, waiting for a sufficient shock to trigger its detonation. Stevenson's analysis had uncovered the how and the why of the gear failure, but the rabbit hole went deeper. The flawed gear was merely a symptom of a much larger disease, a philosophy of profound over-engineering combined with a complete disregard for logistical reality. The core problem, which British engineers at Chobham would summarize in their final reports, was that the Tiger I was a 57-ton tank built on a chassis, engine, and transmission originally designed for a 45-ton vehicle. The added weight, from Hitler's demands for thicker armor, placed an immense, unceasing strain on every single mechanical system. The tank had no reserve capacity. From the moment the engine started, every component was operating constantly beyond its design limits. The transmission was the weak link. American tests at the Aberdeen Proving Ground, cross-referenced with the British findings, confirmed this with horrifying precision. The Tiger's sophisticated, hydraulically controlled Maybach-Olvar gearbox had an expected field life of approximately 100 operating hours. For an active combat vehicle, this is not just poor, it is non-functional. This design flaw was then made exponentially worse by a complete failure of maintenance logistics. When that 100-hour transmission inevitably failed, replacing it was a maintenance nightmare. To access the transmission, which was located in the front of the hull, the entire 25-ton turret had to be removed. This was not a field repair. This was a depot-level overhaul. It required heavy cranes, special tools, and a team of highly skilled mechanics. In ideal peacetime conditions, a transmission swap could take 2 full days. For a Sherman tank, the entire transmission could be replaced by a field crew in under 8 hours, without any special equipment. The Germans, under pressure, had built a tank that could not be maintained. This was compounded by a catastrophic failure to produce spare parts. German industry, focused on meeting Hitler's quotas for new tanks, neglected the production of spares. For every 10 Tiger tanks produced, only 1 spare engine and 1 spare transmission were manufactured. The result was a logistical death spiral. A Tiger would be sent to the front. Within weeks, its 100-hour transmission would fail. If the crew was lucky, they could be towed back from the front, a process that itself required 2 or sometimes 3 of Germany's largest FAMO heavy recovery half-tracks. But with no spare transmission available, the tank would simply be cannibalized for parts or left to rust. The German commanders themselves learned this lesson the hard way. They issued standing orders that Tigers were not to move more than 50 kilometers on their own tracks to avoid mechanical breakdowns before reaching combat. The most powerful tank in the world had to be transported by rail to the edge of the battlefield, driven gently into a pre-selected ambush position, and used as a static anti-tank gun. If it was forced to move, if it was forced to maneuver, if it was forced to be a tank, it would, as one British report bluntly concluded, kill itself. The design flaws extended even to the choice of gears. Allied engineers analyzing the final drives of both the Tiger and the Panther, which suffered from similarly catastrophic failures, noted the use of simple, straight spur gears. These gears are easier to manufacture, but are weaker and handle torque less efficiently than the double herringbone gears used in the American Sherman. The herringbone design provides more surface contact, runs quieter, and is inherently stronger. The Germans knew this. Their own engineers admitted in post-war interrogations that they would have preferred to use a more robust planetary gear system, but they were forced to use the weaker spur gears for a simple reason. They had a critical shortage of the specialized, high-precision gear-cutting machinery needed to mass-produce the more complex designs. This shortage was, in turn, linked to a shortage of tungsten carbide, the material needed for the precision milling tools. Every part of the German war machine was compromised. They had sacrificed reliability for specifications and robustness for complexity. The Sherman tank, with its thicker, looser tolerance double herringbone gears, could absorb the shocks of combat and operate for thousands of hours. The Tiger, a precision-built tight-tolerance machine, was a liability. Its precision was its weakness. A single grain of sand or a slight misalignment caused by a shock load could cause the brittle, untempered components to seize and shatter. Stevenson continued analyzing captured Tigers through 1944. He examined transmissions from tanks built in different months, from different factories. The pattern was consistent. All showed excessive hardness. All showed inadequate tempering. The problem was not one bad batch. It was endemic to Tiger production. After the war, Allied technical intelligence teams systematically documented the German production facilities. They confirmed what Stevenson had deduced. The gears were produced by multiple subcontractors, including the famous firm Zahnrad Friedrichshafen, or ZF. All faced the same relentless pressure: produce more, produce faster. At the ZF-run Waldwerke-Passau factory, which began producing Tiger transmissions in late 1944, the material shortages were at their absolute worst. The molybdenum and nickel were gone. They were forced to make do with inferior steel, which demanded a perfect, careful heat treatment to be viable. Instead, it received the fastest, most abbreviated treatment. Workers described 12-hour shifts with minimal breaks. The heat treatment furnaces ran continuously, loaded, heated, quenched, unloaded, and immediately reloaded. No time for proper temperature verification. No time for adequate tempering cycles. The process that should have taken 16 hours was compressed to 8. One Czech forced laborer, Josef Novak, described the situation in post-war interviews. "We knew the gears were not right," he said. "We could see it in how they looked after quenching. The color was wrong. But we said nothing. We were not German. Why should we care if German tanks broke down? Better that they break than kill people. If we did poor work, maybe the war would end faster." The quality problems were not purely accidental. They were, in some cases, deliberate acts of resistance, sabotage by negligence, allowing the process to drift, not reporting problems, not maintaining equipment.
German supervisors and engineers knew something was wrong. Field reports of transmission failures were impossible to ignore. Henschel's veteran chief designer, Erwin Otters, admitted post-war that they knew the Maybach engine was only designed for a 45-ton vehicle. Using it in the 57-ton Tiger was a calculated risk, a guarantee of reduced engine life expectation.
The German High Command knew. But the pressure from above was relentless. More Tigers, more tanks, more production. Quality problems were acknowledged and then ignored. The priority was numbers. What happened after delivery was not the factory's concern. By 1945, Tiger transmission reliability was so poor that German tank units were actively requesting different tanks. They preferred the older, more reliable Panzer IVs. The Tiger, the supposed wonder weapon, had become a maintenance nightmare, a liability that failed more often than it fought. The German tank crews, who had been told they were invincible, felt the sting of this failure most acutely. The famous Tiger commander Otto Carius wrote extensively about the frustration. His unit's operational readiness never exceeded 60%. At any given time, at least 4 of his 10 Tigers were broken down, usually with transmission problems. For decades, Carius attributed this to combat stress and difficult terrain. It was only years later, after reading post-war technical analyses, that he understood the truth. The transmissions were doomed from the moment of their manufacture. He and his crews had trusted their lives to machines that were fundamentally, fatally defective. The feeling was one of profound betrayal, not by the enemy, but by their own industrial system, a system that chose to produce tanks faster rather than better. Today, this entire metallurgical failure is validated in a very real way. The Tank Museum at Bovington, England, houses Tiger 131, the very tank whose transmission failure helped Stephenson unlock the secret. It is the only running Tiger tank in the world. It is restored to pristine operational condition. But the museum's engineers understand its weakness. They maintain the transmission with meticulous care, using modern lubricants. They limit its operating hours, and, most importantly, they avoid heavy loads. The tank is operated gently, driven slowly, and never subjected to the sharp, pivoting turns of combat. The engineers know that the gears inside are original. They are the same brittle, untempered, low-alloy gears that Stephenson analyzed in 1943. If operated under true combat conditions, it would fail, just as its brethren did. The most famous tank in the world survives today only because it is treated with a mechanical sympathy its designers completely failed to account for. Robert Stephenson retired from government service in 1955 and took a position teaching metallurgy at Imperial College London. He rarely spoke of his wartime work. The memories were complicated. He had saved Allied lives by finding a German weakness, but that weakness existed because an industrial system was consuming itself, exploiting forced laborers to produce equipment that would fail its own soldiers. In 1976, a graduate student named Thomas Richardson, researching tank reliability for his dissertation, interviewed the aging Stephenson. Richardson asked the obvious question: did you feel satisfaction knowing that your work contributed to defeating the Tigers? Stephenson thought for a long time. Satisfaction? No, he replied. The Tigers were defeated by their own inadequate manufacturing. I just documented it. Someone else would have found the same problem. The problem was not lack of knowledge. It was a lack of ability to implement solutions. Germany could not slow production, could not fix the heat treatment. So the problem continued. Stephenson died in 1989. His obituary mentioned his teaching career and contributions to metallurgical science. One sentence mentioned his wartime service, a vague reference to military equipment analysis. There was no mention of Tigers, no mention of transmission gears, no mention of discovering the Germans' most feared tank had a fatal flaw. That information, his reports and analysis, sat in archives, in declassified files, and in Richardson's 1978 dissertation, Reliability as a Weapon. The popular narrative of the Tiger tank focuses on its 88mm gun and its thick armor. But the true story, the one that decided its fate, is not about firepower. It is a story of metallurgy. It is the story of a Rockwell hardness reading of 62 HRC, a microstructure of untempered Martensite, and a catastrophic shortage of molybdenum. It is the story of a weapon that looked invincible, but was crippled not by Allied guns, but by its own gears.